So in this video, I'll be going over number 3 in the second problem set. And here we're talking about cysteine proteases. Proteases are enzymes that cleave peptide bonds. So essentially, the reaction that we have, we're starting off with this. We have the amino acid. So we have this. Okay, that's our amino acid, and we have our cysteine residue, or the cysteine, right? The cysteine protease. So the cysteine, if you remember, is a serine with a hydroxyl group, right? And then that's the rest of the enzyme. And then we also have a base. It says we have a base as well. So essentially, it says that we're utilizing a cysteine residue for a nucleophilic attack of the peptide bond, and we're also having a second amino acid residue that acts like a base for proton abstraction. So we also have the base. So let me draw that real quick. So we have the base. So what's going to happen here? The base will abstract a hydrogen from the cysteine, and that will cause a negative charge on this group right here. Sorry, I might have said serine earlier. I just meant sulfur, the element sulfur, not serine. It'll cause a negative charge here on this element, and then now it will be a very good nucleophile, and will attack the carbon right here. And so that's going to carry out a reaction that will ultimately lead to this. So you'll have this and this. Okay, so we're kind of cleaving, if you notice that we're kind of cleaving the peptide right here. So we kind of have to first find the best base, the identity of the base. That's what A asks for. It says, knowing that the protease shows the highest activity between pH of 4 and 6, what will be the identity of the base? So this is active with a pH of 4 to 6. Okay, so remember the basic amino acids, right? So we have 3 of them using the acronym HACKR. We have H, K, and R. And if you remember your pKa's of these amino acids, you'll realize that H has a pKa of 6. So proteins and amino acids, so basically amino acids, they function at residues, they function at pHs that are equivalent to their pKa's. So they function at environments that are equal to their pKa's or very close to their pKa's. So this should be a so this base, this sulfur group, it acts at a pH of 4 to 6, and so that's when this base will also be very, very good in operating. These have much higher pKa's, and so they won't be as functional as the histidine. So we've established that histidine is our base for the reason that its pKa is very similar to the environment, which is 4 to 6. Okay, so now we have to write the actual reaction. Let me do that. So we have our peptide group. So we have this with the R, and then with the amino group, which is then connected to an R2, R1, R2. Okay, and so what's going to happen, right? So we have the sulfur hydro group, right, which is right here. Okay, and then we have our histidine, and histidine, if you guys don't remember, looks a bit like this. I've also kind of obviously been out of touch with my amino acids, so I'm also looking at the I'm looking at them as I draw them. Okay, so this is histidine. Okay, so what's going to happen? This histidine, it is a base, so it abstracts protons. So what it will do is this right here. This nitrogen is nucleophilic, or basic, right? Same thing, kind of. In this case, because it's going to abstract it's going to attack the electrons here, and it's going to abstract the hydrogen. It's going to abstract the hydrogen from the sulfahydryl group. Okay, so when it does that, you'll be left with a negatively charged group on the sulfur, and so you'll have this. Let me draw it again. You have the amino acid. Okay, but now you'll also have this negatively charged sulfur group, and what that's going to do is it's going to attack this carbon right here. Okay. Now when it attacks and makes a bond there, then you know that carbon can't really have 5 bonds, right? So what's going to happen is it's going to push this bond right here into a lone pair on top of the oxygen. Okay? And what about the base, right? The base had recently acquired hydrogen, so the base will have a hydrogen there. So let me draw kind of the whole shebang, right? So you have the base here now, which will now look like this. So you have the same thing. You have the N. Let me draw the other part of the base first and then get to that last. Right? Now this nitrogen will have an H. And if you guys remember how to do formal charge of an element is basically just the element's the group number, so valence number, minus the number of lines it has, minus the number of dots it has. So in this case, it had 3 lines and 2 dots, right? So nitrogen has a valence of 5, right? So 5 minus 1, 2, 3, 4, 5. That's why nitrogen's neutral here. Here, nitrogen now has 1, 2, 3, 4 lines and 0 dots, right? There's a line between the H and the N here. So knowing that, you know that nitrogen's formal charge now is positive. It's a positively charged entity now. So that's essentially what you have now. Okay. So the result of that, I'm going to come across here. All these steps are reversible, by the way. So now you have this amino acid. Now that lone pair is moved to the top, so you have an extra lone pair, so it's a negative formal charge down here. You also have the sulfur attached to it now. Right, the sulfur. Okay. Now you might be wondering, where did this extra line come from, right? Well, actually, the line here, this line right here, that's actually from the negative charge, the electrons making a bond. So that's not counting for this line, this bond. So this bond resembles this bond right here. And then you have the rest of your structure. So then you have the nitrogen, the H, and then you have the second R group. And so that's kind of the state of the peptide bond. And then with the base, you have this right here. Now let me redraw the base. I wish there was really a way to kind of copy and paste, but I haven't quite figured that out yet, so I'm gonna kind of go with the drawing right now. Okay, so now what's going to happen is that this state's kind of unfavorable. You have an oxygen. I mean, when you see a carbonyl like this, you never see it in this kind of a form, right? You always see it with a double bond, so it's kind of unfavorable. So what's going to happen is this negative charge is due to the lone pair. So what the lone pair is going to do is go back into being a bond. Now carbon can't have, it already has 4 bonds, so once you make that double bond, it'll have 5. So what's going to happen is this bond will sever off as a lone pair, and this lone pair will abstract the H that this base had abstracted in the beginning. So the base will kind of lose the hydrogen it had just gained, because now this is pretty basic too. Nitrogen itself is pretty basic, NH2, NH3, it's pretty basic. So it's going to abstract that hydrogen here. So let me draw that. So let me actually draw the mechanism, right? So this will come down here, and then this will abstract the hydrogen from the nitrogen. Okay? So then you'll be kind of left with what we saw in the beginning. So now I have my kind of have that normal double bond again. The sulfur is still attached. Now, oops, so this nitrogen it's not there anymore, right? So let me undo that. Okay? So that's what I have, and then this nitrogen came off and abstracted the hydrogen, so now it's just NH2R2. Okay, and the base had its nitrogen stolen again, so then I also have the base normal again. So this without the H. Each time I draw it, it gets messier. But that's where we are right now. Okay. So this is where we were. I just erased everything since I wasn't going away, and then I rewrote it at the top. That should be a nitrogen right there. I just forgot to write it in, so I wrote it in after. But we have one more step left with this mechanism. And keeping in mind that it's an aqueous solution, we would know that we have water involved. So then we have water, which is just H2O. So you have this. Okay. So the sulfur hydro group here, you have to keep in mind it's a very good nucleophile. So what that would do is it would abstract hydrogen from the H2O, and when it does that, then you'll be left with this sulfur hydro group as a product. Okay, and then that would create a negatively charged OH group, right? Now this OH group would be negatively charged since it has 3 lone pairs. So then it would be a good nucleophile, and it would attack the carbonyl group, and it would cause the electrons to go up, but then ultimately they'd come back down again. So then you'd be left with this as the carbonyl group. And then the base, we already had figured out. That's just going to also be as the products. So that's the entire mechanism for the reaction. Okay, so that was long. 13 minutes is for A. So let me try to speed by B, C, and D real quick. So B says, assuming that the optimal pH for the reaction strictly depends exclusively on the protonation state of the active site residues, at which pH do you expect maximal enzymatic activity? So at which pH do you expect this reaction to run flawlessly the most? So this reaction has 2 parts, right? The first one is where the cysteine is a nucleophile, right? So the cysteine is a nucleophile, and so we need this cysteine to be negatively charged. We need that. Then we also have the base, right? We have the base, and the base has to be positively charged in the beginning. so that it can first abstract the hydrogen from here. So we need a positive base, and we need a negative. So we need a protonated base and a deprotonated nucleophile. Now we know that cysteines pKa given in the reaction is a pKa of 4. So we know that at a pH higher than 4, this will be negative. Okay. Now we are given that the histidine. We know that the histidine pKa is 6. So anything higher than 6, and that hydrogen will be deprotonated, and then this will become neutrally charged. So we want something less than 6. So we want at a pH less than 6, or less than or equal to 6, because it's already positive still. This will be in its positive state. So we want a pH greater than 4 and less than 6, or less than or equal to 6. So the best way to do that would be the middle ground between the two, right? Which would be a pH of 5. Now C kind of goes along the same lines as this and says, what is the fraction of deprotonated, so fraction of deprotonated cysteine and protonated base at the optimal pH, which we got as 5. So this is where you use a Henderson-Hasselbalch, right? Because we have we want a certain state of the cysteine and the protein. So the way we would set this up is we would have that the pH is equal to the pKa. We know that this is the Henderson-Hasselbalch. So pH is equal to pKa of the log of the conjugate base over the original acid, or over the protonated form. So it would either be cysteine negative over cis, or it can be histidine over histidine positive. So the conjugate base over the original, right? So for the cysteine, we know that the pH, the optimum pH is 5, right? So 5. We know the pKa is 4 plus the log of cysteine negative over cysteine. So then when you work the math out, you would get that this ratio, cysteine negative over cysteine neutral, is equal to 10 over 1. Meaning for every 1 cysteine that we have, we'd have 10 cysteine negatives. But they're asking for the fraction, okay? So this is kind of a weird concept, but it makes sense if I use a simpler term. So if I say that we have a 1-to-1 ratio, a 1-to-1 ratio, then you could tell that it's a 50-50% ratio, right? How do we tell that? Well, we take 1, so it's like the numerator, right? Numerator's on top, denominator's on bottom. So let's say we're solving the percentage for the fraction for the numerator. Then you take the numerator over the numerator plus the denominator. So the total kind of in the bottom. And then you would have 1 over half. So that's how you get the fraction. So in this case, the fraction would be 10 over 11. So do the same thing for the histidine, and you should get the same answer as this. Okay, so that is C. Don't forget to do the histidine part on your own. Let's move this away and do D. So D says, how are these fractions changing at 1 pH unit below the optimal pH? So our optimal pH was 5, right? And now it's going to be 4. So how are the fractions that we just calculated, these fractions that we just calculated, how are they going to change when this is no longer 5, right? So that's what we're trying to figure out. So again, we do the Henderson-Hasselbalch. So for the cysteine, now we know that the pH is 4. So pH is equal to pKa plus the log of the conjugated base, or the abstracted one, over the original, the acid. So we know the pH is 4. We know the pKa of cysteine given was 4, plus the log of cysteine negative over cysteine neutral. And so, this would be 0. So then we know that the log, it'll be a 1-to-1 ratio, right? This is equal to 1. This is equal to 1. So then you know that it would be a 50. It'd be a 1/2 ratio, 1/2 fraction. So 0.5 ratio of cysteine negative. Okay. Now, what about the histidine, right? So the histidine, you know that the pH is still 4. The histidine's pKa is 6. Now on top we have the neutral histidine because it's been deprotonated over the original, which is positively charged. Okay, and so -2 is equal to the log of this ratio. And then when you work it out, you get that histidine over histidine positive is 1/100. So then the fraction of histidine positive, keep in mind that it'll be positive here because the pH is smaller. It's less than its pKa of 6. So that's why histidine positive will have a fraction of 100/101. Now this is saying what fraction of the enzyme will be active. So fraction of the enzyme meaning fractions that will have, which fraction of the enzyme will have both a cysteine negative and a histidine positive. And so you would have to multiply these two probabilities because it's an and. So probability of cysteine and probability of histidine. So then you would have to multiply 1/2 times 100/101 and multiply it times 100 and you would get 49.5%. Now, the big concepts to take away from this and number 4, which I'll be making a video on soon, is just to know just to kind of know how these reactions go in terms of nucleophilic attack and base abstraction, but more importantly, just knowing what a protease is, knowing the various amino acids and which modifications they may undergo or which kinds of reactions they may participate in, and that'll be covered in lecture. So I would consider problems 1 and 2 to be a bit more important in terms of prevalence on the biochemistry exams than this one. But this is good to know because it's a refresher on OChem and it kind of pulls together how enzymatic reactions occur with given environments. So I'll be making a video shortly on number 4, and thanks for listening.